Hello everyone, welcome to my course lesson on understanding JavaScript mutation and pure functions. Now, JavaScript mutation and pure functions are the concepts that we come across whenever we use the Redux in our JavaScript application, especially in Angular, React, or Vue. And also, we come across the concepts of immutability, side effects, and state mutation that we use state mutation and also avoid side effects in our reducer functions so as to be able to manage and also predict our state changes or predict the life cycle of our state. So in this course, we are going to learn about all these concepts in detail, also with examples to learn what they are and how they really boost the performance of our web apps. Now we start by knowing how JavaScript manipulates and access our data types. In JavaScript, values are categorized into primitives and references. Primitives are simple immutable data types, while references are objects that can be changed. The main primitive types are string. They represent textual data. Number represents numeric values. Boolean represents true or false values. Undefined represents the absence of a value. Null represents an intentional absence of any object value. Symbol introduced in the ECMA script 6 represents unique identifiers. Now, on the other hand, reference types include object, a collection of key value pairs, functions, or both. Array, a special kind of object with ordered indexes. Now, function, a reusable block of code. Now, primitives are passed by value, meaning their values are copied when assigned or passed as arguments. References, on the other hand, are passed by reference, meaning the reference to the object in memory is passed. Now, let's look at what happens when we create primitives and also when we create objects. That means reference types. Now, let's say we have a variable 1 like this. So, whenever we do this, what happens in the JavaScript internal stack and heap is that this is a primitive and it will store this variable in the stack. You can see it here. It stores it in the stack. Then this hashtag 000 is the memory address of where it is stored in the stack. Now remember, stack and heap, they are all divided into memory segments starting from 0, 1, 2, 3, 4, 5 to the last. And also same with the heap. So all these stack and heap are all contained in the memory RAM. So the stack is where variables are stored in a push in push out approach. Then heap is also a memory space in the RAM where objects are stored. Now, so when we declared this variable 1, what JavaScript does is to come to the stack and then store the variable name and the value, which is 1 here. So their stack, they are referenced by the values here in the stack so that whenever we use the variable 1, we are typically pointing to each value in the stack at 000 memory address. So whenever we use a primitive, we are just simply accessing straight the value, which is 1. Now, whenever we create an object like this, so what JavaScript does, or what this actually do, is that this object, a reference of it, is created in the stack here. So now a reference of it is created in the stack user, and now instead of pointing to the value, which is this, no, it doesn't do. It points to the memory address in the heap where its value is created. Now it points to 001. Now this is a memory address in the heap. So now let's look for it now. So we see in the heap the memory address 101. And now this is where the object is now created, as you can see. So whenever we reference the user, what we are referencing is the memory address of where it is stored in the heap. So that whenever we use user like this, we are just using the memory reference. Opposite to when we use a primitive that we are referencing its value direct. So whenever we use object, we are referencing the memory address of where it is stored in the heap. So when we do this dot h, so what we are trying to do here is that we are telling JavaScript, go to the user in the stack, then get me its property age. So JavaScript goes to the stack, sees its reference 101, then goes to the memory address of it in the heap 101, and then retrieves the value of the age property, which is 10, and then returns it. So now, when we create another object like user like this and assign it to the user object here. So now what happens here is that a stack is created here now at 002. Now the user object is created here. Now, because of we are making it to point to the user object, now it points to hashtag 101. It points now to the memory address of where the user object of this was created, which is here. So you see now both user object and user object points to the same reference in the heap. You see? So that's why when we do something like this, it returns true, because what this triple equality operator does is to check if the reference of this and this are the same. So it will return true because user object, its reference is 101. For the user object also, its reference is 101. So both of these they are the same despite being stored in different memory address in the stack. Both of them are the same because they all point to the same heap. Now, when we change when we use the user object to change the value of age to 20, now what this does is that it will go to the user object in the stack. Now go to its reference in the heap 101, goes here and change its value to 20. Now it has changed its value uh, from 10 to 20. Now user.age will return 20. User.age will return 20, not 10, because it points to the same memory address. So that's why user.age will give us 20 and user.age also will give us 20, because each of them points to the same memory address, and the user object here was the one that changed the value of this property to 20. We did not use this user object, it was this that did it. But because of both of them points to the same memory reference in the heap, they both point to the same memory reference in the heap. So what this does is just to simply look up via its memory reference in the heap and return the age. So whenever you do this in the user object, it also affects all its references. Now let's say we have also another user object like this and points to the user object like this. Now user object 2 is equals to the user object and also the first user object. All of them are the same, because this will also create a memory address in the stack 003, then user object 2, and its reference will be 101 to this, so that if we change the age property to 30, it will come here and change it to 30, and this will affect all usages of user object and also this user object. So that this is how memory references and primitives objects all work in JavaScript. Primitives works by pointing straight to the stack. Now let's say, let's bring down this here like this. Now Let's create another var, another primitive, and point it to 1. Now, what this does is that it will create a memory address in the stack 004. Now, and it will make it point to the value of the primitive 1. So it will go and read the value of the primitive 1 and point to it. So it points direct to the value of the primitive 1. Now, if we change 1 to 20, what this does is that it will come to the stack of where the 1 variable is stored and change it to 20. So you see the primitive 1 and 2 are different. They point to different values. So you see, so doing this doesn't affect 2, despite assigning 2 to 1. So what this does just to get the value of where this is stored and assign it to 2. Simple. So when we do this, it just goes to where 1 is stored and changes it. So 2 remains 1, while 1 becomes 20. So in this case, 1 is not equals to 2 at all. Now let's say we have another user modified like this. So what this does is that another entry will be created in the stack like this. So for here, it will be 005, then user modified, then it will point at the object created in the heap. So now let's create the object in the heap. So here it will be 102, then it will now have the properties age 90, name John Doe. So JavaScript will now set the reference address here 102. It will set it here. So now you see the user modified is in the stack at address 005 with the value 102. So it holds a memory address, unlike primitives that holds direct value. So if you're coming from the world of C++ or assembly, you will see how that we can assign memory addresses and values to CPU registers. Like we have EAX, ECX, and so on. So that's basically what happens in JavaScript. So the user modified points to 102. So it does not point to 101. So therefore, user is not equals to user modified because they point at different references or different memory references to the heap. User here points to 101, while user modified, the one we have here, points to 102. So the references are not the same. Now, if we do something like this, like in our const user object, we cannot reassign this. So now let's remove this for now so that we can demonstrate how we can change references. Now, let's say the user object was in let, so that we can reassign it. Now, after this, and we reassign user object to user modified. Now, user object will now hold the memory reference of the user modified 102. So what this does, let's clear everything from here up. Now, what this does is that the user object, if you come here, pick the reference of user modified, which is 102, then come here and change it to 102. So that's why user object will not be equals to user modified, because they have the same references in the stack. but this user object will not be will not be equals to the user, because they have now different memory of memory references in the stack. So if we do user object dot name equals to gendo, so what it does is that it will come to user object, pick the memory reference, go to it in the heap, and then change the value of the name property from John Doe to Jane. So in that case, it will affect the user modified also, because they point to the same heap. So saying accessing the name property user using the dot notation or bracket notation like user dot name will return gendo for user modified and also for user object. So you see, so if we also make user object dot age equals to undefined, now what it does, it will come here to the age and make it undefined. So if we delete it also, user object dot age, what this does is that it will come to the heap and delete the age. It will delete it, so that even when we access it via the user modified, it will return undefined. So you see, whatever we do in the user object, it will also affect the user modified, because objects they point to the same references. The objects they point to the same references. So user object points to 102, and while user modified points also to 102. So now in JavaScript, whenever we declare and move around primitives, we are only moving around their values. But whenever we are moving around object references, or let's say whenever we are moving around objects, arrays, or functions, what we are moving around are not the actual value. We are just moving around memory addresses that they point to. For example, this user modified, using looking at our stack, what we are moving around, just memory address 102. Even this object to 101, we are moving around 102. So that is how it works in JavaScript. So, and also that's why it explains whenever we use the triple triple e- equality sign on objects and they return true. So they are not, the triple equality are not actually looking at the value of the object, like checking if age are the same or name are the same. So they are just checking the memory addresses that they point to. If they are the same, it will return true. If they're not the same, it will return false. So that's how the memory addresses and objects work in JavaScript. So object references are stored in a heap, while their value are stored in the stack. So primitives are stored in the stack, whereas objects are stored in the heap. And their pointers are now stored in the stack, which points to the heap. Now note, in stack they are ordered in an orderly fashion. Like when we add something to stack, it it adds that variable or whatever we're adding there on top of the latest addition to the stack. Like if we have this one already, I want to add this, it will add it on top of this. Then whatever we add will be on top of this one, which is this. If we add another thing, it will be on top of this one. But in stack, they are not the same. Stack uses memory allocation to store whatever you want to store inside. Now, if you want to store this, first what it does is that it will run memory allocation to know the remaining memory here in the heap, and then allocates the memory for it and stores it. So now when you bring in another data to store, it will check which site will be compatible and also will be available for this object to be stored. So if it is here, it can just store it here or store it here. So heap stores things on it in a disorderly fashion. So that's why they use the memory allocation memory allocation function for the to allocate memory and store data in it. So you can see that even in C++, we have this mem alloc function. This is what you call whenever you want to create an object in C++ and C. But whenever you create primitives, they are stored in stack, so you don't create any memory for it. So, and then when our program is done, the stack is cleared out because everything is orderly fashion there. But heap are now all the memory are now deallocated. Yes, they are not deallocated, or they might be left when the application starts again. What the program does is to check if a memory if a memory address does not have any corresponding pointer in the stack, it deallocates it. That means it removes it from the heap like this. So that's just a basic way of how the stack and heap work. So if you want to learn more about it, you can search online on how stack and heap works in assembly. I think there's a visual guide on it and a PDF on it that can show you how stack and heap works. Yes, so whenever you use pop, push, uh, all those things, all these things stores their data in the stack, whereas memaloc are stored in the heap. So now we are going to see how primitives and object references work whenever they are passed to a function. Now for this one, we are going to test for primitive. Now whenever we pass a primitive to a function and change the argument, now the change inside the function is not going to affect the primitive because primitive are passed via value like we have already learned. So now we have a variable one which is a primitive with the value 90. Now we have a function with an argument which will pass this variable one into it, and now inside the body of the function we increment it by 100 and assign it back to the value. Now since we are passing a primitive inside this function change, this will not affect the value of this outside variable. Even though we are passing it into the function change, this increment will not affect it because primitives are sent in by values. So what is being sent here is just the value 90, not the actual place where this one is stored. So now let's test it. So you see the first value before the function call, the variable is 90, and after the function call and the change, the variable is still 90 because the change here inside the function change will not affect the primitive because it is passed by value, not by reference. Now if we pass in the object user, now let's first log the user, and then we'll change the value of this age inside it like this. Let's say value dot age, let's change it like to 20 now. And now let's log it after the change. Now because of this is an object, it is passed by reference. Now this change to its property will make the actual change to this object here, because what is being passed here is not this value, it is the address of where the user is stored. For example here 101, so it's just like we are passing in change the address 101. So you see, JavaScript will look up the value of this in the stack and the value is 101. So it passes this 101. So whenever it hits here and makes this claim, so JavaScript knows that yes, this is an object and whatever it is holding here is a memory address. So it goes to the memory address 101, which is here, and makes the change to 20. So now this will now print out an object with the property value to 20, no longer 90. Here we print it 90, but here it will be 20. Now let's check it out. So you see, at the initial stage, before the call, the age property is 90. But after the call to the change user, to the change function, and the age property is changed to 20, now it affected the object. And now, after the call there, the user was now changed and the age is now 20. The actual change that was done inside this function. So that you see that whenever we call a function and pass an object to it, what we are passing into the function is the object reference, and it will point to that object that we are passing into, and whatever change being done in the object and inside the function will affect the object and whatever that is pointing to it. So if we need to keep this immutable, we need to pass a clone of it. We can use the rest parameter. So this now creates another object like this. It will create another object like this. It will create another object. Now inside it, it will be 102 with the same property age 90, and then now store it in the stack. 006. Now store it in the stack pointing to 102. So this is what happens here now. So what it is now passing into it is memory address 102. Memory address 102. So it will come here, change the property. What it will do, it just come here, it hits here and change it to 20 without touching this. Without touching this at all. So when we log the user after this call, the age property will still remain 90 instead of 20. So when we run it again, you see it's 90. See, it's 90. Yeah, because we created another object and passed its reference to it. So our original user was not affected. Now let's come to state mutation. Now the mutation is simply when the properties of an object or an array is changed. You know, in biology, we have DNA, and those DNA encode for proteins in our body. Let me say a protein called proteinase is encoded by the DNA sequence ATGC like this. So now this now codes for this protein. So now whenever the body or the cell sees this DNA, and you know DNA is deoxyribonucleic acid, so this is just the code to create a protein. So you see the sequence of this. So this exact sequence is what is needed to create this proteinase that gives us nutrients in our body. Now, if any of this encoded sequence is changed, like for example, instead of A here, T is added, it will no longer produce this protein. It will produce another one. Let me say xylinase. So you see that the former DNA has been mutated. So in biology, we call it DNA mutation. So this mutation is still the same logic we have in JavaScript. So let's say this object encodes for state of anybody. Now, this state object encodes for the name of a user, John. Now, if we come and change the state to this is now a state mutation of this object. So it has now been changed. Anywhere this object is being used, the name will no longer point to John, it will now point to Jane. So this, either using dot notation or bracket notation, we have changed the property and the property of the object name from John to Jane. So this is called state mutation. Same thing we have in an array. So we have 2, 3. If we do something like this, or let me say 0, point it to 1, we have changed the value of this first element from 2 to 1. This is called state mutation. So we have changed now the sequence of this from 2 to 3. Now it will now become 1, 3. So you have changed the state from this to this. So the change directly affected this, the variable array. Also coming to here, the state change here affected the object state. So it's no longer named John, it will now be state, it will now be name Jane, and the age 90. So we have changed the state of this object from this to this. So this is what state mutation is all about in JavaScript. Now, this state mutation, it is not really good because one, whenever we change the property of a state, it creates another hidden class in JavaScript. But this will be for another video where we explain JavaScript optimization. And also, whenever we change this, it introduces another state to the object, and any way in our application that depends on this state will have its name being changed. And also it makes this untrackable and this unpredictable, because either of this can change and we don't know when and how. So this is where immutability comes in. Immutability is just a concept or a state whereby an object or object references cannot be changed at all. So it just comes that we cannot change object references like this object state and array. But if we want to change it like this, we need to create another object and then make the change. So now, to change the property of this name to Jane, we will no longer do this. Rather, we will create another state like this and then now make the change. So still now preserving this state. Also, in array, still the same thing. Instead of this, we just simply create another array and then make the change 1, 3. So this is called state preservation or immutability. The immutability that we have been hearing in Redux and not, this is what it means. Instead of changing this original state, we create another state from it and then now make the change instead of effecting the change internally in that object or in that array. Now, let's say this is the central state in our application. Now, we don't want this to be mutated. Now, and we have our reducer function here like this that takes in a state. Now, this reducer function acts on this state here, depending on the action being sent to it. So inside this reducer state, we don't want a case whereby we can mutate any of the properties inside the state. For example, let me say is like set age. Now we don't want to do something like this state dot age to be the payload of the action. Now let me remove this so we can see it very well. So we are mutating the state here. So we don't want this to happen. So what we want to do is that we will create a new state like this, then change the age property. So now this should not be done because this is mutation. With this, we preserve the state of this and makes this our reducer function to be immutable. So with this, we know that we are not changing the state, that for every action on the state, it returns a new state. So we use the rest object or the rest property to render everything inside this state object into this object that we created, and then by so doing this, we will now set a new value of age property. So this is how we maintain immutability of an object or an array. Now let's look at pure function. If a pure function is a function that depends entirely on its functional scope, it does not modify any external variable or depend on any external variable or any other global state. And also its output is dependent on its input. Now let's look at an example of a pure function. Now this function add is a pure function. Why? Because first, its output is dependent on the input. Look at it, returns the summation of two numbers, and now these two numbers are the numbers passed to it. So you see that the output is dependent on whatever that is passed into it. Now also, it does not modify or change any global variable or any variable outside the scope or any environmental variables. So its work is self-contained. It does not depend on any other variable outside of its functional scope within these brackets. So this function is highly predictable. So whatever we pass to it, we can predict what it will return. So we predict it will return 9. If we pass this to it, we predict it will return 10 and it will return 10. So these are the characteristics of a pure function. They are predictable, do not depend on external state or modify an external state. Now let's look at an example of a impure function. Now this is an impure function because it depends on an external state. This date dot now is not defined inside this functional scope. It is a static property defined in the date object, which is outside of this function scope. So you see, whatever affects this date will surely affect this function, and its output is non-deterministic because we don't know what it can return. It returns the current time, but what it will return here is not what it will return here, despite both of them running at the same time. So you see, it is non-deterministic, and also its output does not depend on its input at all. So examples of impure functions are just functions that side effects. For example, functions that we used to subscribe to observable streams, we used to subscribe to WebSockets, we used to make HTTP requests, look up for dates, and also functions that modify or depend on external variables. Like now, for example, let's say we have this variable global var 90, and we have this function, let's call it impure function. Then it takes an input. Yeah, you see, in as much as its output is dependent on the input, it is not a pure function, because the output also it depends on a global variable. Now let's look at this impure function again. So in as much as the output depends on the input, it modifies a global variable and also uses the global variable too. If we remove this, it's still an impure function. And also, if we do something like this, like getting the environment variable, it's still an impure function, because this environment variable is not defined within the scope of the function. So it still depends on this, which is an external variable. So this makes this function an impure function. So now one of also the basis of, or the goodies we get from pure function, is to make it memoizable. Now memoization is an optimization trick whereby the results of an input are returned if the inputs occur again. So this makes the execution time of the function the second time after the first or the initial call to be almost instant. So it reduces the time and makes it faster the next time the same inputs are called. So you see that pure functions are good candidates for memoization. Yeah, you can check my YouTube video on memoization, whereby I talked about everything memoization, what memoization is, with examples, and how we can memorize so many functions like the Fibonacci factorials. So all these are pure functions that are memoizable. So pure functions can also be memoized, and they add a very huge optimization boost to applications. So whenever we are writing our code, make sure to write pure functions wherever needed, so that we can be able to memorize our function and boost the performance of our application generally. So this comes to the end of our course, understanding JavaScript mutation and pure function.